Good morning. This recording is for Algebra 1, Chapter 9, Lesson 3, Finding and Estimating Square Roots. So, a lot of you are semi-familiar with square roots. They look like this symbol here, and it is what we also call a radical symbol, and it indicates a square root. Square roots are basically the opposite of squares, okay? So a square would be like some number to the second power, okay? So, a radical symbol, also known as the square root symbol, the number or symbol indicates that the square root is the radicand. So basically, the radicand is the symbol or number inside of the square root, all right? And we're basically trying to figure out what times what gives us the number inside the square root. So we have principal square roots, which are basically anything to the positive, anything that's going on with the positive square root. So positive square root of 64 is 8 because 8 times 8 is 64. And then we can have the negative square root, which is the opposite of the square root of 64. Well, the square root of 64 is still 8, but then the opposite of that would be negative 8. Make sense? All right, and if we're going to show both, we're going to use the plus or minus the square root of 64, which means we're going to have a plus or minus the square root of 64, which is 8. And if it ever has the plus or minus in it, your answer also has to have the plus or minus. Usually we use this as a range. It's either plus 8 from a certain point or minus 8 from a certain point. We're talking about the plus or minus. There's a lot of ways it can be used. For right now, just know that if the square root has a plus or minus in front of it, then your answer also needs to have a plus or minus in front of it. So make sure that you pay attention to that, all right? And then again, that's the plus or minus symbol. So if we have the square root of 49, what times what is 49? Well, most of you should know that is 7. So there you go. So 7 is the answer for that. All right, number 2, plus or minus the square root of 225. What times what is 225? Well, that would be 15, plus or minus 15. And number 3, okay, so whenever you have operations inside of square roots, usually multiplication or division, you can actually separate the square root so that you'd be like, all right, well, if I need the square root of 1 over 25, I can actually take the square root of 1 and the square root of 25 and then divide them. And so just pay attention to that. You can break things down inside square roots, just like you could probably break them down using like the distributive property and a few other things. So let's go ahead and take a look at this. What's the square root of 1? Well, 1 times 1 is 1. And then the square root of 25, 5 times 5 is 25. Therefore, it's basically 1/5. The square root of 125 is 1/5. All right, and again, we can do it with multiplication too. We can say that the square root of 196, well, 196 is the same as the square root of 4 times 49, and we already know what the square root of 4 is. Well, it's 2, and the square root of 49 we've already done, which is 7. So it basically ends up being the square root of 4 times the square root of 49, which ends up being 2 times 7, 1 simplified, and 2 times 7 is 14. So the square root of 196 is 14. And so that can actually allow you to do perfect squares that you might not be familiar with immediately. If you can think of 2 perfect squares, and perfect squares are numbers that when you do multiply them together, usually integers that you multiply together, you're going to get, perfect squares out. So things that when you do take the square root of them, you get an integer out. There you go. Okay, so I believe I have one more example. And that's the square root of 24. Well, 24 is 4 times 6, and you could probably also done 3 times 8, but 3 times 8, neither of them are perfect squares. So if you can remove a perfect square from a situation, do so, and that's actually called simplifying. So if I can break 24 down into 4 times 6, well, 4 is a perfect square, so I can take the square root of 4, and I can multiply it by the square root of 6, and I'm going to get 2 times the square root of 6 because the square root of 4 simplifies even further. So even though I can't pull the square root completely out of 24, I can pull something out of it, and that just allows you to simplify things a little better, or a little easier, or a little more. Okay, I think we're moving on. And I simplified each expression on the previous page, so we don't need to do that. All right, so we're going to tell whether expression is rational or irrational. And remember, a rational number can be written as a fraction or as a terminating decimal that doesn't repeat. Whereas an irrational number can be, well, is written as decimals that don't repeat, or basically, don't repeat and then don't terminate. An example would be pi. Pi goes on forever and it doesn't repeat, and it is like our most iconic irrational number. Okay, so let's go ahead and see if the square root of 8 is rational or irrational. Well, if you were to stick the square root of 8 into your calculator, you're going to get an irrational number. And basically that's because the square root of 2 goes on for bloody ever. Forever, ever, ever. Okay? All right, number 2, plus or minus the square root of 25. Well, that gives us plus or minus 5. 5 is an integer, therefore it can be written as a rational number, because 5 over 1 is 5 as a fraction. And it definitely terminates if you ever were to divide 5 by 1. Yeah. All right, number 3, we have the opposite of the square root of 75. Well, I can take the square root of 3 times the square root of 25, and that's going to give me negative 5 times the square root of 3, which is irrational because, again, if you take the square root of 3, there's not an integer that if you multiply it times itself, you're going to get 3, so it is definitely irrational. Right, number 4, we have the square root of 1/4. Well, the square root of 1 is 1. The square root of 4 is 2. 1/2 is rational. It doesn't repeat. Well, it doesn't repeat, but it also terminates. Therefore, it is irrational. All right, so just some things to remember to memorize. The square of integers are called perfect squares. You need to memorize them. Most of you have them memorized already. Most of you know what they are. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81, 10 times 10 is 100, 11 times 11 is 121, 12 times 12 is 144, 13 times 13 is where I start to get a little sketchy, but I think it's 196. But you should definitely have memorized 1 through 12, so you can just quickly recognize those perfect squares. All right, it's going to help you a lot, especially if you ever have to estimate. So estimating perfect squares between what two consecutive, by the way, that's supposed to be consecutive. There we go, consecutive, there we go. Consecutive integers is, well, we want to do negative 105. Well, if you think about it, we know that the perfect square of 10 is 100 and the perfect square of 11 is 121. Well, 105 just happens to be between them. So the square root of negative 105 is between the square root of 100 and the square root of 121, which means that's the in between the square root, in between the answers of negative 10 and negative 11. But it's probably a little closer to negative 10. So if they had to have you pick one, I'd probably round down to negative 10. So there we go. So the opposite of the square root of 105 is between negative 10 and negative 11. Bam. So again, it's really good if you memorize those perfect squares up until a certain point, just because they could come in really handy, especially if you're estimating. Okay, so here's another one. We have the square root of the square root of 380, and it's between the square root of 361 and 400, which is 19 and 20, and that means that the square root of 380 is between 19 and 20. It's actually probably closer to 19, I'd say. 380 closer to 361 than it is 400. It's 19, 20. Yeah, it's probably close. It's probably right in the middle, honestly. But you know, unless you want the exact number, you're gonna have to do it in your calculator. All right, so excuse me, it's a little early. I stayed up watching the Olympics last night, the Winter Olympics, by the way. All right, so. The formula d equals the square root of x squared plus 2x squared gives the length of d of each wire for the tower at the left. Find the length of the wire if x is 12. Okay, so basically we have this structure, and it forms a triangle, right? It forms a triangle right there. And we know that the height of the triangle is twice the length of the base of the triangle. And we basically want to find the hypotenuse. And this is something we're going to get into a lot more next chapter. And when we get into geometry, you guys are going to have to be experts at finding the hypotenuse. But the hypotenuse is the side that is across from the right angle of a triangle, and I like to think that there's an arrow coming up out of that right angle and it's pointing to the hypotenuse, and that's just how I remember. But this formula that we have here is the square root of x squared plus 2x squared is going to give us the length of that hypotenuse. Okay, so let's go ahead and fill in the blanks with what x is. So we're going to take the equation and we're going to fill in where 12 goes, and we're going to simplify. So distance equals the square root of 144, because 12 to the second power is 144, and we have 2 times 12, which is 24, which is 2 to the second power, which is 144 plus 576, which means we're taking the square root of 720, and that means we're going to get roughly 16.8 feet. Again, we don't need a big honkin' decimal for this. It is going to be irrational because there's no integer that if you square it gives you 720, so therefore we do need a round. Okay, I'm going to stop now because this should have been even then a little shorter. All right, bye guys. Sorry so long. They've all been long. I apologize. Bye.